Today we want to remind ourselves about the thinking that goes around integration, and then we can start building mechanics around integration. Integration is multiplication, but one of the factors is variable. For example, area should be length times width, but in the figure that we've drawn here, the length is variable. Here it's all small when x equals a, but when x equals b, the length is all tall. So the length is variable throughout the width. Since we don't get to use multiplication because the length is not constant, we could think of multiplication as repeated addition. That's the fallback position for multiplication. Multiplication is what we get to do when all the terms are the same, but all the terms are not the same. So we have to drop back to addition. Then we run into the other problem. The function, or the length, is continuously changing from x equals a to x equals b. It's not changing by steps. There is no next real number that we get. It's continuously changing. So we got to drop that back as well. We got to drop back this continuous change to a discrete change so we could put pluses in between everything. Our strategy for that is to assume that f of x is constant for some small pieces of the width that we'll call delta x. Once we flatten out the function for small changes, we can just view this as a bunch of rectangles. And over those small delta x changes, we're assuming that the function is constant, so we get to use multiplication. And then we just add up all the areas of those rectangles. We assume that the function is constant, then we get to use multiplication and then just add up all of the results. The big change is going from the discrete sum to the continuous sum. In the discrete sum, there's a next rectangle where we use a constant value of the function for the height. But in the continuous sum, there's no next real number. We can't count things by real numbers. Because if I start the counting at 0, there's no next real number. But when we're counting rectangles, first rectangle, second rectangle, third rectangle, there's always a next rectangle. No matter how small we make them, there's always a next one. So there's the discrete. We got to flip over to the continuous. The way we do this is we set up our discrete sum and then look at what happens if we just use, as we use more and more rectangles. That's how we take limits at infinity. We just look at what happens when we do more and more and see if it's flattening out. Are we approaching some limit as the number of rectangles goes to infinity? If we are, then we declare that to be the limit and say that is the continuous sum. Any questions? It seems like a lot to think about, but that's only because it's a lot to think about. It seems like I've said all these things before, but that's only because I've said all these things before. We don't get songs stuck in our head by hearing them once. We get songs stuck in our head because I just keep reading you the lyrics and then you get sick of hearing it because then you can't unhear it. All right. So let's review our strategy where we assume that f of x is constant for small pieces of the width. So then we get to use multiplication, and then we'll see what our sum looks like. So what we're going to do is we're going to look at a function. I have to decide if this is going to fit. If I flatten out the function, it'll fit. So we're going to have some function. That's a little bit too flat. Our length is all variable between x equals a and x equals b. But what we're going to do is we're going to break this into pieces. And I'm going to break it into thirds because I need practice breaking things into thirds. And what we're going to do is we're going to flatten out the function. So between x equals a and this first value, let's name this let's not name these. We don't have to name them. We're going to break this region up into, sorry, this interval up into 3 little delta x's. So for these small changes in x, we're going to assume that the function is flat. The way we do that is we just pick a value of x in each of these subintervals and use the value of the function at that point as the height of the rectangle. So in each subinterval, we pick a value of x in each subinterval, we choose a value of x and evaluate the function at that point. Evaluate the function at that x and use the value of the function as the height of a rectangle. Use that value of the function as a representative of the height of the subinterval. So we are going to index these x's and make them stand out. We choose a value of x, and I'm going to index it x sub I. Then we evaluate the function at that x sub I. And so f at x sub I is the height of the rectangle that we use for that approximates the subinterval. Hopefully there was a sentence in there. So I'm going to pick a point x in this first subinterval. I'm going to call that x1. Then I'm going to pick any point in here that's going to be x2. And then I'm going to pick a representative here, x3. I evaluate the function at each of these points and say that the function is going to be flat. I'm going to say for this delta x, this first delta x, instead of the function being all changing like this, I'm going to just make it flat. That's what I'm looking at. That's how I'm looking at the function. So there's f at x1. Then I go on to the next rectangle, and I evaluate the function at x2 and say that is going to be the height of my rectangle. I'm just going to use this value of the function. And now f is constant on this second delta x. Then I'm going to do the same thing in x3. I pick a value in that subinterval. I evaluate the function at that point. And there's f at x3. So now I have 3 rectangles where their height is given by a value of the function, and the width of each of the rectangles is delta x. So the area is f at x1 times delta x plus f at x2 times delta x plus f at x3 times delta x. Since the delta x is being multiplied by all of these, it's convenient for us to factor it out. So we factored out the width, and we have the sum of these 3 lengths. We're still looking for the area under the curve. And there's a little bit of, this under here is a little bit of underestimate. We're missing some. And here's a little bit of overestimate. These won't necessarily balance out, but there's a little bit of overestimate by adding some up here and a little bit of underestimate by missing some there. And in each of these cases, there's a little bit of underestimate. Here's a little bit of, sorry, a little bit of overestimate and a little bit of underestimate. So what we're doing is we're just flattening out the function. If we want an underestimate, we could just, since the function is increasing, if I just pick the left endpoint and flatten it out, then we'll be under the whole time. That's what we were doing yesterday modulo this class. But here we just have values of the function representing the lengths of each of those rectangles, and the delta x representing the width of each rectangle. So there's the delta x, which we can factor out. It's the width of each rectangle. And here are values of the function representing the lengths of each of those rectangles. So there are the values of f that are the lengths of each rectangle. The delta x is the width of each rectangle. We factored the delta x out because that first area, this first area is going to be f at x1 times delta x. The second rectangle is going to be f at x2 times delta x. Then the third rectangle will be f at x3 delta x. So I wanted to factor out the delta x. Any questions? One of the things that we want to notice here is that we are just adding up a bunch of values for the function. We're just evaluating the function at a bunch of points and adding up those values. This represents some weight that we're using. And this helps us kind of fit this adding the values of the function up into our area under the curve narrative, where we're just doing rectangles. So notice the values of f are the lengths of each rectangle. We are just adding up the bunch of values of the function. This is the discrete sum in the discrete sum up here. This is our approximation. What we need to do, since here, this is where we see the next rectangle and the rectangle after that. We need to turn this into a continuous sum where I can't even write f at x1 plus f at x2 because there is no next real number. This is our discrete sum. And all we're doing is adding up a bunch of values of the function. Any questions? So that's our plan. If I want, so now there's some, like I said, there's some overestimate and some underestimate. Maybe that's canceling out. Maybe it's not completely balanced. But if we use, instead of 3 rectangles, if we increase the number of rectangles to 4 rectangles, then these little bits are going to get smaller. Because the closer we look at the function, the flatter the function is. And the closer we look at a function, the flatter the function is. So even if we are looking at a crazy function that looks crazy steep, is not that crazy, it's just a polynomial. But if we zoom in, the closer we zoom in, oops, I'm going to lose my function. The closer we zoom in, the flatter the function is going to get. I picked one that's really steep. So I should have picked something flatter. The closer we zoom in, the flatter the function is going to look. Just like we're standing on the curved surface of the Earth, but we're so small compared to the curve that we're standing on, we don't see the curve. So much so that some people are denying that it's even there. All right. So here's our plan. Let's see how this ties into the new thing. So let's come up with some notation and then see how this is tied with something that we already know. That's derivatives, and specifically doing derivatives in the other direction. Let's actually pause the video here so we can get a break and we don't get a super long video.